So this video is about lesson 2, probability axioms and some properties. So in lesson 1 we already talked about the the operations of sets. We have the union, the intersection, and the complement. Okay, so this time we're going to have the key concepts. Let S be the sample space and let A be any event of S. The probability A, denoted by probability of A, we are using a capital letter, is a real number satisfying the following axioms. Okay, so the first axiom states that the probability of any event is a value between 0 and 1 inclusive. Okay, the second axiom, on the other hand, states that the probability of the sample space to occur is 1. Hence, in itself, the sample space is called a sure event. Moreover, the third axiom states that if A and B do not have common elements, then the probability of their union is just the sum of their probabilities. Okay, so when you say do not have common elements, that is mutually exclusive. Okay, that was discussed in our last one. So another thing is probabilities can be approached in the following three ways. So letter A, priori or classical probability. Here, the probability is determined even before the experiment is performed. It requires equally like outcomes and assumes that a given procedure has n different simple events and that each of these simple events has an equal chance of occurring. Thus, the probability of an event A, P of A is defined as probability of event A is equals to the number of sample points A over the sample points in S. Okay, so that is what we call the priori. Okay, so and second is posteriori or empirical probability. Here, the probability is determined by repeating the experiment a large number of times. Thus, if we're going to get the probabilities of this A, we have the number of times event occurred over the number of times the experiment was conducted. And then, the subjective probability is determined by one judgment of intuition. In most cases, the probability is found by simply guessing or estimating its values based on the knowledge of relevant circumstances. So these are the following approach or three ways in probability. So let's take the example. So let a card selected at random from an ordinary pack of 52 cards. Are you familiar with 52 cards? The one that we use in Tong-It, in Unggoy, like that. So let A be an event of getting a spade. So what is a spade? So we have here a spade. This is a spade. Okay. So let A is getting a spade, and let B is an event of getting a face card. So what do you think are the face card? Okay, so this is also an example of a face card. So we have the spade and we also have the space card. Okay, so how are we going to get the probability of A? So in getting the A, we know that in A we have spade when we are doing the baraha. So we have 2 to 10, di ba? 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 9, right? 9. Then we have a queen spade plus jack spade and king spade. So we have 3. So 9 plus 3, that is 12. So that's why we have y is 13. What else? Queen, jack, king. Alas. Yes, the alas or the 1. So we have 10 plus 1 and we have 13. So we have here 13 over 52. That is the sample space. So 13 over 52. Okay, so that is the sample space. So 13 spades out of 52 cards. So we have here 1 point. Okay, that's how we get 13. Okay, so the number, let's have the probability of B, where B is an event of getting face cards. So probability of the number of face cards, we have Queen, Jack, King. This is not included. So King, Jack, Queen. So we have spade, hearts, what else? Spade, hearts, diamond, and what was that? The kalamunggay. There are 4. So fourth, we have the queen, we have the jack, and we have the king. Since we have 4 shapes or types, we have the what's this? We have the heart, we have the diamond, we have the spade, and we have this one. So we have 4 times 3, we have 12. So that's why we have 12 over 52. Okay, so that is 3 over 14. Now if we want to know the intersection of the probability of A and probability of B, or the event A and the event B, so how are we going to get that one? So we are just going to get the number of spade face cards. So what are the number of, since the probability of A is a spade and the B is face cards, so we're just going to get the intersection, diba? We are going to get the intersection since the spade has also a face card. So we have a spade queen, yes, spade queen. We have also the spade king, and we also have the spade jack. So we have 3. So we have 3 over 52. Hence, the intersection of the probability of A and probability B is 3 over 52. Okay? So, how about if we have, you try to answer this one. Okay. So, you have tried to answer this one. Okay, let's have a next example. The probability that an even number appears in a toss of a fair die. So again, we're talking about the fair die. So the sample space of that one is, we have 1, 2, 3, 4, 5, and 6. So fair die. So even number, so we have 2, 4, 6. So 2, 4, 6. So we have 3 over the sample point, which is 6 sample point. Okay, so we have, that's why we have 3 over 6, and that is equals to 1/2. So the probability of an even number appears in a toss of a fair die is 1/2. Okay, next is a king appears in drawing a single card from an ordinary pack of 52 cards. So when you say king appears, so it doesn't matter if it is a heart, a spade, a diamond, or a club. So basta kay king, so meaning there are 4 shapes man, so we have 4 over 52, or that is equals to 1/3. Okay, that is the probability. Next is a white marble appears in drawing a single marble from an urn containing 4 white, 3 red, and blue marble that is 4 over the sum of all the marbles inside the urn. So we have 4 plus 3, 7 plus, so that is 4 over 12, or that's equivalent to 1/3. Suppose we are going to get the probability of the red marbles. So we have red marbles is, we have 3 over 12, which is equivalent to 1 over 4. How about if it is a blue marbles? Probability of blue marbles, we have 5 over 12. Okay, so that's it. Now let's move on to the next example. Let 2 items be chosen at random from lot containing 12 items, of which 4 are defective. So given that we have 12 items, but there are 4 defective out of those 12. So what do you think is the number of non-defective? So since the total item is 4, so 12 minus 4, So 12 minus 4, that is equals to 8. So that 8 is the non-defective. Okay? So let's have the event. Let A be the event of that both items are defective, and let B the event that both items are non-defective. So since the experiment is to choose 2 items from a lot of 2 items, then the sample space S can occur in, okay, so we have it could be, first we have to get the total. Yes, first thing is there is no restriction, meaning it could be defective or it could be non-defective, so that's why we have 12 combination of 2. So what is again the formula of combination? We have combination n combination r is equals to n factorial over r factorial, and the difference of n minus r factorial. So that's why we have 12 combination of 2, because we are going to choose 2 items at random from a lot containing 12 items. Okay, so by this, if there is no restriction, it could be defective or non-defective. So we have what's this? We have 12 factorial over 2 factorial, and then we have what's this? 12 minus 2 factorial. So we have 12 factorial over 2 factorial times 10 factorial. That's equivalent to 12 times 11 times 10 factorial over 2 factorial, and then 10 factorial. We just simply cancel it out, and then we have, what is 12 times 11? We have 132 divided by 2. We have 66. That is 66 ways. So we are going to have 66 ways in getting 2 items chosen at random from a lot containing 12 items. So there is no restriction if it is a non-defective or defective. Okay, so how about if we want to know if, let A, say for example we're going to get the probability of A, we have the event of both items are defective. So go back again. So since we are going to talk about defective, both items are on the defective, so we are not going to use 12 because we are just going to make use of the defective. So since there are 4 defective, then we're going to get 2 items, so that is 4 combination of 2. Okay, so again, so we have now, again, we did not use 12 because there is a restriction that it was only we're going to get 2 items from the defective, so that's why we have 4 combination 2, which is 4 factorial 4 factorial over 2 factorial, then 4 minus 2 factorial is equals to 4 factorial over 2 factorial and 2 factorial, and then 4 times 3 times 2 factorial over 2 factorial then 2 factorial. Okay, so that is 4 times 3, that is 12 divided by 2, that is 6. So in getting that one, there are 6 ways in getting 2 defective out of 4 defective. So we have 6 over 66. This is our probability of A. Again, this 6 is only for defective items, and this 66 is the total, or the sample space, or the sample point. Okay, how about letter C? How about we find the probability of B, which we're talking about here, non-defective? Again, we are not going to use 12 because we are just going to get 2 items from the non-defective, which is non-defective is 8. So we have, this is B, huh? So we have 8 combination of 2. So we have 8 factorial over 2 factorial. The difference of 8 minus 2 factorial is equals to 8 factorial over 2 factorial, then 4 factorial. So that would be 8 times 7 times 6 times 5 times 4 factorial over 2 factorial and 4 factorial be cancelled out, and then you have now 8 times 7 times 6 times 5. 8 times 7 times 6 times 5. We have 1680 divided by 2. Oh, wait. Yeah. Oh yeah, my fault. Let's go back. This is 8 minus 4 is 6 factorial. Yeah, that is 6 factorial. That's why. 6 factorial. So we have here this. So we have 6 factorial. So we have to cancel. So now 8 times 7 is 56 divided by 2, that is equals to 28. So there are 28 ways that we can get 2 items from the non-defective. Okay, from the non-defective. So we have the probability of B is equals to 28 over 66. Okay, so again, how are we going to discuss this 28? So there are 28 ways we can get 2 items out of 28 ways of 2 items out of 8 non-defective. Okay, so that's why we have the probability of B, which is 22 over 66, and the probability of A is 6 over 66. So we have this. Okay, so that is equivalent to 1 over 11. Simplified it first, and 14 over 2. Okay, so that is how you're going to get the probability. So next, the last example. The probability that a student passes statistics is 0.60. The probability that he passes chemistry is 0.85. If the probability that he passes at least one of the subject is 0.95, what is the probability that he will pass both courses? So we are given the probability of passing statistics is 0.60, chemistry is 0.85, and the probability of at least one, so meaning that is union, or so at least one of the subjects is 0.95. So how are we going to get the probability that he will pass both courses? So we are looking for, we have the formula here, P, alright, P union B. P union B is equals to P event of A plus event of B minus the A intersection B. Okay. Alright. This is something wrong. Since this is intersection, so we are given the union. So we have here, if we are given the union, so therefore we are going to have the intersection both months, so we are using and, so that refers to intersection. So we have the formula here, P, the probability of the union of the event A and B is equals to the probability of A plus the probability of B minus the probability of the intersection A and B. So since we are looking for the intersection, so we are using probability of A intersection B is equals to probability of A plus the probability of B minus the probability of A union B. Okay, so that is what the formula that we're going to use. So let A be the stat. This is your A, this is your B, and that is for what's this? Intersection. So you have now the probability of stat plus the probability of chem minus the probability of the union of stat and chem. So you have now 60.60 plus 0.85 minus 0.9. So we have here 50. So the probability of that he will pass both course is 0.50. Do not forget to put piliin. Do not forget to put piliin. So again, therefore, the probability that he will pass both courses is 0.50. Okay, so that's it. So